Hi guys, this is Dr. Gnanachandra, Center for Research and Postgraduate Studies in Mathematics, Ayya, Nadar, Janaki, Ammal College, sivakasi. In this video, we are going to see contraction mapping in metric spaces. First, let us see the formal definition of contraction mapping. So, for that, I have taken first the metric space M, and both domain and codomains are M also. See here, and this is a mapping T from M to M. I'm going to say T is a contraction mapping. Then I have to find the distance between any two elements in the domain, that is distance between x and y in the domain, and T of x, that is the image of x and image of y. I'm going to connect the distance between x and y and the distance between T of x and T of y. That is, a mapping T is said to be in contraction distance between T of x and T of y less than or equal to alpha times the distance between x and y. Here the alpha is taken as less than 1, that is alpha less than 1, and x and y are belongs to M. So a mapping T from M to M is said to be in contraction satisfying this condition with alpha less than 1. Okay. Now let us see the example of contraction. For that I have defined a function t from closed interval 0, 1 by 3 to closed interval 0, 1 by 3 in the real line, a piece of closed interval, and a mapping is defined by t of x equal to x square. This is a mapping and I am going to prove that this mapping is a contraction mapping. Okay. For that, I have taken x and y for any two elements in the closed interval 0, 1 by 3. Therefore, the maximum distance, that is the maximum value of x is 1 by 3 and the maximum value of y is also 1 by 3. Now, I am going to find out the distance between t of x and t of y. We have already defined t of x equal to x square. So, in the real line, we are considering the usual metric. Therefore, distance between t of x, t of y equal to modulus of t of x minus t of y. Okay, so here I have applied the formula of t of x equal to x square and t of y equal to y square and split this one into x plus y into x minus y. I already pointed out that the value of x less than or equal to 1 by 3 and y less than or equal to 1 by 3. Therefore, x plus y less than or equal to 2 by 3. So I have applied here this value and this can be taken as a d of t of x comma t of y less than or equal to 2 by 3 into modulus of x minus y. So modulus of x minus y can be written as d of x comma y. Finally, we get d of t of x comma t of y less than or equal to 2 by 3 into d of x comma y. Here alpha can be taken as 2 by 3 and this value is less than 1. So this mapping T satisfies the requirements of a contraction. So the mapping T of x equal to x square in closed interval 0, 1 by 3 is a contraction. In the similar way, we can prove that T of x equal to x by 2 is also a contraction mapping, and T from L2 to L2 defined by T of x equal to x and by 2 is a contraction mapping. And we all know that L2 is a collection of all sequences. Therefore, we take two elements, X and Y in L2. They are nothing but their sequences. And also, we can use the formula of distance between any two elements in L2 as summation n equal to 1 to infinity x minus y the whole square to the power 1 by 2 divided by 2. So, I have applied that formula here and I get this value of d of t of x comma t of y equal to this, and I can take out 1 by 2 outside and this can be written as d of x comma y because x equal to xn and y equal to yn. Here alpha equal to 1 by 2, that 1 by 2 is also less than 1. So this function also satisfies the requirements of a contraction mapping. So this function is a contraction. Okay, next let us see another example. T from closed interval 0, 1 to 0, 1 be a differentiable function. If there is a number alpha with alpha lies between 0 and 1 such that t dash of x less than or equal to alpha. This is a condition and t is a mapping from 0 closed interval 0, 1 to closed interval 0, 1 where t dash is the derivative of t. Then with this condition t is a contraction mapping. We have to prove this example by we are using mean value theorem. We all know the mean value theorem, that is t of y minus t of x equal to y minus x into t dash of z, where z is lies between x and y and x and y are lies in the interval closed interval 0, 1. So I have applied the modulus of t of y minus t of x, which is nothing but modulus of y minus x into t dash of z. The condition given in the example is modulus of t dash of x less than or equal to alpha for any x belongs to closed interval 0, 1. See here, z also lies between closed interval 0, 1. Therefore, modulus of t dash of z less than or equal to alpha. So, we have applied this condition and we get the requirement of a contraction mapping. So, this is an example for a differentiable function to be a contraction mapping. Okay, next one. This is a theorem of connecting contraction mapping and continuous. Yes, every contraction mapping is continuous. So first we have applied the definition of a contraction mapping here. Simply we can write it d of t of x comma t of y less than d of x comma y. It's a special condition of, particular case of contraction. And we have take epsilon greater than 0 and choose the value of delta equal to epsilon. Then d of x comma y less than delta. That is whenever d of x comma y less than delta implies d of t of x comma t of y less than d of x comma y. But d of x comma y less than delta, but delta equal to epsilon. So combine this d of t of x comma t of y strictly less than epsilon. So we get the definition of continuity. So every contraction mapping is continuous. So we will use this theorem and we have to prove fixed point theorem, that is contraction mapping theorem. Okay, this is a statement of contraction mapping theorem. Let MD be a complete metric space. Note that, guys, this MD be a complete metric space and T be a contraction. Then there exists a unique point x in M such that T of x equal to x. That is, T maps x into x. This means T has exactly one fixed point. So for this reason, this theorem is known as fixed point theorem or contraction mapping theorem. So I have assumed M be a complete metric space and T be a contraction. Then with these conditions, there exists a unique element x in M such that T of x equal to x. So to prove this, we have take x naught be an arbitrary element in M and we have assumed that x1 equal to t of x naught and x2 equal to t of x1, x3 equal to t of x2, iteratively xn equal to t of xn minus. So we have taken these two things. Our aim is to prove xn is a Cauchy sequence. I have constructed sequence xn and I'm going to prove this xn is a Cauchy sequence. So why I have to prove this is a Cauchy sequence? Because I have in the theorem they have given MD be a complete metric space. So I have connected Cauchy sequence and a complete metric space. We all know that in a complete metric space every Cauchy sequence is convergent. So for I'm going to reach that concept. First I'm going to prove xn is a Cauchy sequence. Okay. For that I have to use first T is a contraction mapping. So this is a definition of contraction mapping. We already saw this one. Now I'm going to find out the value of d of xn comma xn plus 1. Guys, I already assumed that xn equal to t of xn minus 1. Okay. And xn plus 1. Using this we have defined xn plus 1 equal to t of xn. So iteratively we'll apply this. So xn t of xn minus 1, xn plus 1 t of xn. Okay. Now using contraction, this definition, distance between t of x comma t of y less than or equal to alpha times the distance between x and y. Here distance between t of xn minus 1 comma t of xn, this is less than or equal to alpha times d of xn minus 1 comma xn. That's all. So next we have applied xn equal to t of xn minus 1. Therefore, xn minus 1 equal to t of xn minus 2. And we have applied this one. We can get it alpha into d of xn instead of xn minus 1 we have substituted t of xn minus 2, okay, and xn t xn minus 1. Again we apply the definition of contraction, that is this definition. We get this alpha into alpha times d of xn minus 2 comma xn minus 1 and the inequality becomes less than or equal to. So we will reach through contraction and these iterative assumptions. Okay. And then proceeding like this, we can get that finally alpha to the power n into d of x naught comma x1. So we get d of xn comma xn plus 1 less than or equal to alpha to the power n into d of x naught comma x1. Okay, now I am going to prove xn is a quotient sequence. For that, I have to take d of xn comma xn, generalized triangle inequality. I have used it here. That is xn, xn plus 1, distance at xn plus 1 and xn plus 2 up to xm. I have assumed m and n are two positive real numbers, positive integers, and assumed the condition m greater than n. Okay, now I have to supply the value of this using the above iteration process one by one, and this d of xn comma xn plus 1 becomes alpha to the power n into d of x naught comma x1, and this one becomes alpha to the power n plus 1 into d of x naught comma xn, and so on. Finally, we get. In these terms, alpha to the power n into d of x naught comma x1 is common, so we took outside, so it will become this like. Okay, here I have applied the value of strictly less than because alpha to the power n into d of x naught comma x1, and I have taken 1 plus alpha plus and so on. That is infinite sum. Here the sum is finite, but I have taken infinite sum, so the inequality becomes strict. So d of xn comma xm now alpha to the power n into d of x naught comma xn into 1 minus alpha. Now, already we assumed that alpha lies between 0 and 1. Therefore, the sequence alpha to the power n converges to 0. Using the definition of convergence, we can get this alpha to the power n into d of x naught comma x1 divided by 1 minus alpha less than epsilon. Because alpha to the power n converges to 0 means distance between alpha to the power n comma 0 which is less than epsilon. But I have assumed that this positive quantity also less than epsilon. So this quantity less than epsilon, we supply this one here and we get that d of xn comma xm which is less than epsilon. This shows that xn is a Cauchy sequence. Okay, now xn is a Cauchy sequence, but in the theorem itself they have given m is a complete metric space. In a complete metric space, every Cauchy sequence converges, therefore this sequence converges. Again, given T is a contraction mapping, and we all know that contraction mapping is continuous, therefore T is continuous. Now we have two conditions. One is xn converges to x and T is continuous. So in the characterization of continuity in terms of sequence converging to a point, T of xn converges to T of x. So here I have written T of x equal to limit n tend to infinity T of xn, limit n tend to infinity xn plus 1 as per definition of T of xn, and hence x is a fixed point of it. So I got it T of x equal to x. Now final part is I'm going to prove this point is a unique fixed point. So suppose I have taken another point y belongs to m such that T of y equal to y and y not equal to x. Y not equal to x means the distance between x and y greater than 0. Okay guys, now d of x comma y equal to, as per our assumption, x equal to t of x and y equal to t of y. Therefore, which is less than or equal to alpha times d of x comma y. So we get that d of x comma y into 1 minus alpha less than or equal to 0. But d of x comma y is a positive quantity. So which shows that 1 minus alpha less than 0, which is a contradiction. Because we have assumed alpha less than 1, that means 1 minus alpha greater than 0. So why this contradiction occurs? We have taken another element y belongs to m, that is also a fixed point. So this shows that this contraction mapping theorem has only one fixed point. Therefore, x is the unique fixed point. So we have proved that the contraction theorem, that is m is a complete metric space and t is a contraction, then t has a unique fixed point, that is t of x equal to x. So in this video, we established what is the definition of contraction and some of the examples, and the main theorem is contraction mapping theorem or a fixed mapping theorem. Okay, I think you have understand the concept, guys. Thank you.